Hello everyone, I'm Jae-Gol, one of the instructors of this course. This is the first lecture in fifth week, and we will continue studying the linear algebra, and in particular we study eigenvalue and eigenvector. And the goal of this lecture is to understand those eigenvector and eigenvalue concept, and also the null space and characteristic equations to solve these eigenvalues. And we will study how to find all these eigenvalue and eigenvectors from a given matrix. So let me start with the definition of eigenvalue and eigenvector. So we initially start with a square matrix A in n by n dimensional space. And we consider some special vector called eigenvector as this non-zero vector x in n-dimensional space, such that this equation is satisfied for some scalar lambda. So in this case, lambda can be chosen as any value as long as it satisfies this equation. And in that case, lambda is called eigenvalue of matrix A, and such a vector x is called an eigenvector corresponding to a lambda. Let's understand the characteristic of this eigenvector from the transformation perspective. So let's consider a linear transformation Tx, which is defined by Ax, where A is a given matrix. And then if x is an eigenvector, and then this Ax will be represented as lambda x, which means the output vector has the same direction as x, because this vector is just a scalar multiple of vector x. So in general, A times x will actually change both the direction and the length of the input vector. But in the case of eigenvector as our input, and then even after this transformation, the vector direction will still be the same, but only the length will change. So let's look at one example here. So given A as this matrix, and then suppose this is our eigenvector. We didn't study how to obtain this eigenvector, but let's just suppose that this is an eigenvector and verify if it is true. And let's compute A times x, and then it will be A comma 8, and then it will be scalar multiple of the original vector x by a scaling factor of 8. So we can now obtain Ax equals 8 times x when using this particular vector x. So geometrically, this is our input vector, and this is an output vector, which is in the same direction, but the length has been changed by the scaling factor of an 8. So in this case, the vector x is called eigenvector, and this scalar value corresponding to the place of lambda is called eigenvalue. And in general, if we apply apply this matrix transformation by using maybe another vector, minus 1, 1. And then the resulting vector will be 4, minus 2. So in this case, we can clearly see that this vector and this vector is not in the same direction, and also the length is different. So in general, both of the length and the direction will change after this transformation. But in the case of this eigenvector, only the length will change, but the direction will remain the same. And this eigenvector equation has some computational advantages in terms of matrix vector multiplication. So let's think about which computation is faster between these and this. So in general, we have a matrix A and X, and this is a general transformation defined by our matrix A. But if this is the same as lambda times x. And then, yeah, this is such an example based on the previous example that we saw in the previous slide. And then if we compute this guy, then we have to compute the inner product between these, and also these and these. So in general, we need to have 2 multiplication and 1 addition. And also for this vector, we need to have another set of 2 multiplication and 1 addition. So in total, we have 6 multiplication or addition. But in this case, we can only compute just 2 multiplication, right? So the latter case will be much faster than the previous one. So if we know our vector input vector x is an eigenvector, and then the matrix transformation will be really efficient by utilizing this eigenvector equation. Okay, then let's look at this eigenvector and eigenvalue equation that we have to satisfy. And this equation can be rewritten in this form. Okay, so we have matrix x, A and x here, and then it should be lambda times x. And then we can write it as this form, right? And then now let's change this matrix. So let me rewrite it here, A times x. Let's change this part as, so this is lambda. So we have a lambda here. And then let's put some identity matrix in the middle, x. Okay, so this identity matrix is just having all ones along the diagonal and zeros on the off diagonal elements. Okay, and then we can factor it out by matrix A here minus lambda and identity matrix times vector x. So this should be 0, and that way we obtain this new equation. Okay, and then this equation actually gives a new linear system where we have the matrix B defined by this. So this entire part is our matrix B, and we have matrix vector x here, and then we have a 0 vector here, right? So this is our new linear system, and I mentioned that this vector x, which is our eigenvector, should be non-zero vector here. And why do we need to restrict eigenvector as non-zero vector? This is because of some practical reason. That is, the vector x, if the vector x is 0 vector, and then the eigenvector should be having the same direction even after the transformation. But if we use a 0 vector, and then essentially it has no direction. So there is no sense of preserving its original direction. So that's why we exclude a 0 vector. So back to this equation, because the given vector B is a 0, and so we know at least one solution is all 0 vector x here, but we restricted our eigenvector as non-zero vector, and thus it is called our trivial solution for this linear system. And then the eigenvalue lambda is the one that makes A minus lambda I, which is our matrix B, that has a non-trivial solution for this equation. So originally A times x equals 0 may not have any non-trivial solution, but after A minus lambda I, and then this matrix B should have non-trivial solution or non-zero vector as a solution for this equation. And such a value of lambda will be called eigenvalue. Given this equation, the set of all the solutions of this equation is called a null space of a matrix A minus lambda I, which we call a eigenspace of A corresponding to lambda as our eigenvalue. This eigenspace consists of zero vector, of course, because zero vector satisfies this, and all the other eigenvectors which are non-zero vectors corresponding to this particular eigenvalue lambda. Okay, then what is this null space? So the definition of the null space given a matrix M by N is the set of all the solutions of Ax equals 0. Okay, and this equation, when in particular B is set as zero vector, is called a homogeneous linear system, and we denote this null space of A as null of an A. And then we can understand the conditions that this vector x should satisfy, okay, in order to make this equation to be true. And then we consider A composed of these row vectors. So now we consider each rows of matrix A, and then if we multiply the vector x here, then this guy times this should be 0, and thus we obtain this, and this guy and also the same guy should be 0. Okay, and thus we obtain these set of equations, and it means this guy is represented as this. So A1, or the first row vector, should be orthogonal to our solution vector x, and A2 should also be orthogonal to x, which means that our solution x should be orthogonal to all the row vectors in our matrix A. And this is the condition that we have to satisfy the vectors contained in our null space. And one interesting theorem about this null space, which is that our null space is actually a subspace. And if you remember the condition or requirement for the subspace, and that was this subspace should be closed under the linear combination of the two vectors. So we can prove that easily. Suppose we selected the two vectors from our null space, and then by the definition it should satisfy these two conditions. So the first selected vector is x1 and the second one is x2. And then let's think about the linear combination. It's this, and the transformation with the A. And let's check if that is also a zero vector. And we can distribute this guy into here. And then C1 times A and x1 plus C2 times A x2, right? And then this part will be 0, this part will also be 0, and thus it will be 0. So clearly it is closed under the linear combination. And because this null space is a subspace, we can think of it as some span of some vector, some basis vector. And then the number of the vectors contained in the basis that spans our null space will have a particular number, and that was called a dimension of this subspace. And so this null space can be one-dimensional, containing one basis vector, or two-dimensional, that is spanned by two basis vectors. And also the condition to be a basis vector is that they should be linearly independent, of course. Okay, and then let's get back to eigenvalue and eigenvectors. And let's think about this example where we have to show 8 is eigenvalue of this matrix And then also we have to find the corresponding eigenvector. And let's form A minus lambda I, where lambda is set as 8. And then A minus lambda I is this matrix, and then times x is 0. And yeah, this one is minus 6x1 plus 6x2 is 0, and 5x1 minus 5x2 is also 0. And we can easily obtain the solution that satisfies this as this vector 1, 1. And then its a scalar multiple will be also the solution. For example, 2, 2, 3, 3, or minus 1, minus 1 will all satisfy these two equations. And so, in this case, the null space of this is the span of the single vector. That is, the eigenspace containing all the possible eigenvectors corresponding to this eigenvalue is the subspace spanned by this vector. And in this previous example, there exists another eigenvalue, which is a minus 3 in this case. And then let's verify that is also true. And A plus 3i is obtained by this matrix. And then we have to obtain the solution that satisfies this new equation. And then we can easily obtain the solution as this vector 1, minus 5 over 6 that satisfies this equation. Okay, similarly, the eigenspace containing all the eigenvectors corresponding to this lambda, which is different from the previous example, is the subspace spanned by this basis vector. And then now the question is how we can find the eigenvalues such as 8 or minus 3. And those eigenvalues should guarantee that the corresponding linear system gives a non-trivial solution, which is our eigenvector. And then this matrix should be non-invertible. And let's think about the situation where this is not true, where this matrix is invertible. And then in this case, we can multiply its inverse matrix on the left, and then we obtain x vector as always 0 vector. So in order to have the solution as non-zero vector, this A minus lambda I should be non-invertible. And in this particular case, we can determine whether A minus lambda I is invertible or not based on something called this determinant. And if you remember the 2 by 2 case where A was A, B, and C, D, and A inverse had this formula, and we consider the situation where A inverse is not existing, which is this guy was 0. So the denominator in this part is 0, and then the matrix A is not invertible, and this is not 0, and then it will be invertible. And this kind of criteria to determine whether matrix A is invertible or not can be defined for larger matrices, more than 2 by 2 matrices. So that is called this determinant, and this determinant of A minus lambda I should be 0, so that this kind of denominator becomes 0. And in that case, matrix A minus lambda I will be not invertible. And so our eigenvalues should satisfy this equation, and this equation is called a characteristic equation. And also, from the sense that A minus lambda I times x equals 0 has multiple possible solutions. So we have, by default, a 0 solution. And if we have other solutions which are non-zero solution, or our eigenvector, and then it means this equation will have multiple possible solutions. in that case, we learned that the corresponding coefficient matrix should have linearly dependent column. So when the matrix is a square matrix, and then that square matrix has a linearly dependent columns, and then it means the matrix is not invertible. Okay, so back to our previous example, let's construct our characteristic equation. But let's first verify the determinant of the original matrix A. And then we compute the determinant by this form, and then it is non-zero value. So the original matrix A is invertible. But if we use A minus lambda I, which means we subtract some common value lambda from each of our diagonal elements, and then the resulting matrix will be non-invertible, which means its determinant will become 0. And then let's just apply the determinant formula in the case of 2 by 2 matrix, which is AD minus BC. And then this is an AD and this is a B times C, and then if we evaluate this equation, and then we can obtain the solution for this equation as minus 3 or 8, which were our eigenvalues that we observed in the previous slides. After obtaining each of these eigenvalues, and then we construct this equation that we have to satisfy in order to obtain eigenvectors. Okay, so again, for each lambda, we construct this equation and then solve for x, and then obtain those non-zero solution. And such a non-zero solution is called eigenspace, and then also it is a kind of null space of matrix A minus lambda I. And then we also prove that the null space is some subspace which is spanned by some basis vector, and such a basis vector can have more than one vectors, which means eigenspace can be 2 or more dimensional, not just a one dimensional. So let's think about this two-dimensional eigenspace. So suppose this is our eigenspace corresponding to a particular lambda as 2. And then it will have many possible vectors contained in this subspace. And all of them are actually our eigenvector that satisfies this as 0. And then here lambda is 2. And then each of vector in this subspace or this eigenspace should satisfy this relationship. And thus, if the vector was this vector, and then the vector direction will not change, but the length of the vector will be just 2. And this vector will also have the length by a scaling factor 2, but the direction will remain the same. So this is a property of all the possible vectors contained in this eigenspace. And in summary, we can find all these eigenvalues and eigenvectors by following these steps. So first, we can find all these eigenvalues by solving this characteristic equation written by here. And then once we obtain these eigenvalues, then for each eigenvalue such as 8 or minus 3, and we use each of these eigenvalues and then construct this equation and then solve for the solution for this equation, and then we obtain the set of basis vectors corresponding to eigenspace, because using those vectors, and then we can obtain any possible eigenvectors corresponding to this equation. So in summary, in this lecture, we covered eigenvector and eigenvalues, and also we considered this characteristic equation to obtain all these eigenvalues. And then for each of these eigenvalues, we obtain eigenvectors corresponding to those eigenvalues. Okay, thank you very much.